here in the Black Lab. So I'm going to be talking about my efforts to build a protein complex map in Pseudomonas, which is an opportunistic infector that infects a lot of people that are severely immunocompromised, such as patients in the hospital or like burn patients, and also people with cystic fibrosis. So the outline of my talk is pretty basic. I am going to talk a little bit about efforts that's not included in this in building a conserved bacterial protein complex map, but that will just be sort of touched on lightly. And then also just like I want to use this as sort of an opportunity to get some feedback into the current map and some of the difficulties I'm having and like maybe some ways forward. So the question is, why more bacterial protein complex studies? There have been several. There have been about 10 in various different species. The most widely studied being E. coli, which has 3 or 4 separate high-throughput protein interaction studies, as well as a lot of small-scale studies. So one reason is that there are a lot of different bacterial genes. For instance, in Pseudomonas has about 5,800 different proteins, and there's not a lot of overlap between the Pseudomonas genes and the E. coli genes. And so this leaves a lot, like a potentially very large space of bacterial protein interactions. That,
so
yeah.
Genes or proteins at this level that they're comparing?
This is comparing at the gene level.
At the genome.
Yeah. So this is the sources of ortholog database. I'm taking this one. So and that's why I was out of order. My apologies. But so why Pseudomonas exactly? So I already mentioned sort of that Pseudomonas has this clinical relevance, but it also has like a large genome. There's 5,800, relatively large for bacteria, and it has a very large metabolic diversity, and it's an opportunistic vector. Here on our system, our healthcare system. So the pipeline for finding new protein complexes should be very familiar to people who have been coming to these talks and hearing Kevin, Claire, and hopefully they'll talk about chemical fractionation aspect. But essentially, taking Pseudomonas and grow it in this artificial sputum. So it's an artificial sputum that's developed to mimic the spit of cystic fibrosis patients. And we did chemical fractionation mass spec and some machine learning on these chemical fractionations to infer the protein interactions, and then cluster those protein interactions to get out novel protein complexes. So also, in addition to just growing sort of typical lab strains of Pseudomonas, have also started growing some, doing chemical fractionation on cells taken directly from CF patients. So that adds some clinical relevance. So far, it's hard to read. I apologize. It's always hard to tell like if it's going to show up or not. But on the top is the number of mass spec experiments, and Pseudomonas on the left, and E. coli separations. I've also done some separations in E. coli, and so I have over 650 individual mass spec experiments for Pseudomonas and about 300 experiments for individual mass spec experiments for E. coli. And these are the number of separations. So there's about 15 separations for Pseudomonas, and then I have about half that for E. coli. And then plotted here is the number of proteins that I'm observing genome-wide. So, all right. So this is a total. Sorry, the one on the left is the total number of proteins, which is 5,800. This is the number I'm observing. So I'm observing about 4,000, and then without E. coli. So this number is taken when I map the E. coli proteins onto these Pseudomonas.
So
genome. Yeah.
they are the ones that are not together with similar with E. coli proteins.
Yeah, a lot of these have no ortholog.
Okay.
So interpretation of that? Bars? I didn't quite get it.
These are the number of proteins that I can see in the mass spec experiments.
So on the left is
this is the total number of proteins
In the genome.
in the genome.
Okay.
Yeah, and then potentially we could see, and I'm seeing about 4,000 of the. That's a pretty good coverage. Right? It's like
Yeah, it's excellent. Of the Pseudomonas ones, and then on the right.
on the right, this is without, if you don't consider the proteins that are observed in E. coli that are mapped onto the Pseudomonas.
So there's a few hundred proteins that are the only evidence.
Only evidence comes from orthologs of E. coli, but they're not really necessarily being expressed in the Pseudomonas that I have in my hands. Please remind me of separation. Yeah, so doing chemical fractionations. So you lyse the cells and then run them through a chemical gradient. So like separating things on size or based upon charge.
So size exclusion chromatography,
Yeah.
HPLC.
So there's 12 unique. What you're trying to say? There's 12 unique kinds, or there?
Which separations are you doing?
So I'm doing a wax spec type, which is an ion exchange. I'm doing size exclusion, and I'm doing isoelectric focusing, which and all these different separations, they have slightly different conditions. So in some cases, I'm doing membrane prep, so I'm doing membrane preps with different detergents to try to extract more membrane proteins. Or they were grown in different conditions, like different media. So there's this artificial spit medium, or they're growing healthy. So they're all slightly different to try to build evidence for connections. If you see proteins. Yeah, that's what I'm saying.
So this is 3 unique types of separations. Several
Other
different preparations.
parameters.
Membrane, size,
So here I've just plotted some of the separations for the ATP synthase complex. So here's a heat map, and each of these blocks is a different fractionation experiment, and elution time going down. And then the darker the green, the higher expression is for that given row. So you can see the big chunk of the ATP synthase is sticking together across many different fractionations and experiments. And the these here on the right, the ATP, F, G, and H, these are membrane transmembrane proteins, so they're a little bit more difficult to. They aren't observed as much, and they don't stick together.
Are they enriched in your membrane fraction?
Yeah, so some of them. So you can see. Let's see.
What is a membrane?
Yeah, LDM is like this one. These have a little bit higher correlation. This is a membrane fraction. DDM is also a membrane fraction. They tend to stick a little bit better together. It's not, and then like these two proteins stick together better than Triton X, and they're probably stick together as well. So it's hard to say, like, sort of systematically. It's better, but I mean, because there's not really necessarily great annotation for which proteins are membrane proteins and which ones are not.
A, B, and C, is that the F1? This is
Yeah.
F1, F0 together? Or what is the-
Yeah, it's F1 and F0
So the,
together. It's all the ones that I've observed in F1 and F0.
so FG and H, is that the F0 and then A, B, C, the F1?
Yeah. Yeah, so you got, I think you said it. These are the membrane proteins, and then these are the ones that are in the supplements.
But are the membrane ones known to form a compound?
Yeah,
You expect them to be a compound?
yeah, as well known. Yeah, there's a structure for
Or
this.
ATPA is constructed. That's the one.
I actually have the structure later on. Or cartoon, please. But yeah, the question.
Yeah, I was just curious, are they alluding on the size distribution at about the right size?
Yeah.
So the Tritons with the detergent, do you expect that to become bigger? Is that evolution time is going down?
Yeah,
things should go
so the larger things are eluting earlier. So these in the Triton X, these guys are sticking to more proteins. So like it's shifting up is shifting larger.
So, I mean, is that expected? I don't think I've looked at a lot of them.
I think there's in the membrane in preps there tends to be a little bit more like non-specific binding, like for the individual preps to like other membrane proteins. So it's like clumping together with
With
stuff.
the Trimax or without?
With the yeah.
Do you see, are these subcomplexes as well? Like different types of these complexes?
Yeah, so there's the F1 complexes are C and D, and then there's like that's in the cytosol, and then and the membrane is the F0. Same complex.
Yeah.
So there is hierarchical structure in this data as well.
For example, IEX has multiple bands, some showing only 3 subunits, some showing many more subunits.
Yeah.
That might suggest subcomplexes or different types of them.
Yeah, I think that there is definitely some information about subcomplexes in this data. I know Kevin has done a lot of work into trying to extract subcomplexes systematically. I think that it's difficult. It's a difficult problem. But if you know what the structure is already, then you can kind of, in retrospect, kind of makes sense.
So there's a correlation structure on subunits.
So I've sort of talked about this a little bit more in detail. I think let's move on to how I'm training. So I take these evolution profiles and I build correlation features based upon this and train it in a machine learning framework. So my training data is taken from E. coli gold standard complexes, which is pulled from the EcoCYC database, mapped to the Pseudomonas strain using eggnog, and then I split the training and test set at the level of the complex. So after mapping, there's 166 complexes and about 570 positive interactions, which is kind of low actually, and it might be leading to some issues in the confidence of the interactions I'm pulling out. Well, I'll talk about that later. So yeah,
Is that after the split, or is that before the
it's 570 before the split.
before level 2 and less?
Yeah. So that's in total. So it's not. It's a little bit underpowered for machine learning. Perhaps. So the features, like I said, were the elution profiles, and then I take the correlation on these elution profiles, and I'm also calculating the z-score on the correlations to try to reduce reduce indirect interactions between proteins that are pulled out. And then I'm also using co-expression from RNA-seq, so using the NCBI Geo and human samples that are requested from Margot Lively lab, so they took actually burn samples from burn patients and directly from sepsis patients, and then did RNA-seq on the Pseudomonas. And yeah, I'm also taking the genetic distance between pairs of proteins for their genes. So that is learning some sort of operon structure. So the idea is that for bacteria, a lot of proteins that are in the same operon tend to complex together. So,
Sorry, how many total complexes are in those USC?
oh, there's a couple hundred.
Is that what it's
Oh, okay. There's a couple hundred.
Oh, so like you're not
Yeah, it's
losing a lot.
not losing a lot, but it's like half of them are pairwise interactions. But this is like the only gold standard that I really know of. It's not from a high throughput study. So the sort of scheme that I've taken is I was concerned about biasing my results if I were including the expression and genetic distance, that I was concerned that I would just get back mainly all interactions that were within an operon. So I done this analysis on features with and without expression, and also with and without the E. coli chemical fractionation mass spec. And I did it without the E. coli chemical fractionation mass spec because I also wanted to make sure that I wasn't biasing towards necessarily conserved genes, because the non-conserved genes are actually the more interesting from a clinical aspect, because those are the genes that are responsible for making Pseudomonas virulent. So I did this analysis pipeline where I did a feature selection using random forests, and then did SVM to train, and then predict. Did the two-stage clustering. So there's a soft clustering on the protein interaction network, followed by a hard clustering to break up large complexes. And then I pruned interactions that did not have direct MS evidence from my data set. So I require that all interactions that I see have some strong correlation across more than one experiment. And then I just merged the complexes from all these different techniques.
The feature selection, what was kind of the rankings? Were the ones that are obvious?
Yeah, well, so in the case where I included expression and distance, those were the most dominant features. There was otherwise there was like kind of a mix like of size exclusion and ion exchange, and isoelectric focusing tended to be pretty low on the list. And then membrane prep, some of them were better than others.
Is there any sound correlation features? So those are good.
Really? I
Over Euclidean.
over Euclidean. So I did the experiment correlation, but now this was sound.
This one's useful with, especially some of the data sets that have low spectral counts.
Yeah, because you're adding the noise.
Yeah, exactly. So you're compensating for that.
Yeah.
And some of the data is from
So I could do that for the I could do that for the MS too.
Do you know how the people set complex map was made? Did they use
It's literature curated direct evidence from small scale experiments.
Literature evidences.
From
It
small
does not include genetic distances.
no. These are all from small scale experiments. There's very solid evidence for all the interactions. These are well-known complexes. So a lot of them have crystal structures. So this is an overview of the complex map, and you can't really see the lines between these dots, but I've colored the essential genes in orange, and there are about 2,000 interactions among 1,600 proteins, and a lot of these are pairwise interactions, and you can see this on the size distribution. So this is the complex size on the x-axis, and then the percentage of proteins.
Number of proteins?
No, so this should sum to 100. So it's normalized, so that I can compare the red is the gold standard size distribution. So I'm getting a more pairwise than the gold standard.
Your number of your complex size is number of components?
Oh, right. Number of proteins in that complex. Right. Not like Dalton's. And I'm recovering the number of. So these are the for those that I have co-annotations of. I'm recovering a good number of membrane proteins, 181, or integral component of membrane, whereas compared to 206 are labeled as cytoplasmic. And then various number of other compartments.
Can you use proportions of membrane and cytosolic for background proportions?
Yeah,
I
I
guess that membrane would be 150%.
did plot that. So I plotted the
It seems pretty enriched for membrane.
yeah. So I plotted the percentage of proteins in each compartment. So so this is the outer membrane. I'm getting like 50%, and cytoplasmic I'm getting like 60%. Periplasmic I'm getting a lot of the periplasmic.
So you're seeing, this is not weighted by abundance, that was just counts. So
Yeah, it's just if it's observed.
you're seeing 4, 6, it was 4,000 over 6,000, or less than 6,000 proteins overall. That's the overall sampling rate in the experiment.
Yeah. So I'm seeing about it's about 40%. It's not
So
like
60%.
not all these numbers are about even, right? Except for like these fibrinal proteins.
So it's not like in paraplasmic, it's like you're sampling it without the background.
Yeah. Yeah.
So the membrane is under
A little, but not dramatic.
Well, they're expected to be much less.
But usually, and if you just do, you don't make concerted effort to do membrane prep studies, it will probably be lower.
Not capturing film.
Yeah, I think that they're kind of fragile, so I'm doing heating and I'm probably just ripping them off.
What's it do?
It's involved in cell motility. Like it extrusions from the cell that help the cell move around, and sometimes they attach to other cells. And, so I just wanted to show some examples of known protein complexes. So this one is actually in the map, but I thought it was kind of, it is in the, sorry, this one is in the, is actually in the training set, but it manages to get the hierarchy of the complex correct. So these L and then A, J, K, H are in the membrane, and these are clustered together. It's so hard to read up here. Yeah, so these are clustered together up here. And then yeah, BFG, which are down here, clustered down here, and then these guys in the middle are actually interface. So there is like sort of this hierarchical relationship, like structured in the data. Moving out. So this the ATP synthase, which I showed you earlier, was not included in the training set, and again, you kind of see this hierarchical relationship where the cytosolic parts are clustered together, and then the membrane parts are clustered together too.
So the F0 is the barrel down at the bottom, or am I misremembering?
Yeah.
Is that all F1 that you're seeing?
This is all F1 that's coming in the cluster. It survives the cluster, and then you have the stock ATB and F right here.
What's the missing component? What's the
barrel is I forget what the protein name is. Let's see. There's A, B, C, so there's E, ATP, ATP.
and you're not seeing from that?
It wasn't really. It was wasn't correlated very highly with the other ones. So I could see it, but the correlation with these other ones was low. So I'm also using this guy. So this is just the elution profile of the complex. I already showed you the ATP synthase one. But this is just to show that these raw elution that they're sticking together.
Are there two different places where they come up? Is that what we look at?
Oh, sorry. So these are a bunch of, so each of these blocks is a different separation.
Okay.
And then each of the row is a different protein in the complex. And so I've colored different, each of these blocks has a different color. It doesn't really show up.
So
Or each of these rows have a different color.
What's the second and third row?
Yeah, the second and third row are new of B and F.
Okay, you go back to the structure. Let's see B.
Yeah, so B and F, but they're probably just indirectly connected.
Where are they in your map?
Oh, yeah, so B is here, and F is here, and there is a connecting line between. So I did some alternate validation on this set also. Comparing to the gold standard, the leave-out set, the precision and recall, and then also comparing to the string database. So this is taking interactions from several different databases and literature and curating it all together. A lot of these interactions are from high throughput studies. And then, so the different rows are just the raw interactions. And then the second one is filtered on MS evidence, so I'm requiring MS evidence. And then the third one is after clustering. So after clustering, we lose a few interactions. And then, so for the precision and recall, for precision for both the gold and the string database, they seem to be pretty high, and then filtering bumps the precision up even higher. And then at the cost of recall. And then the enrichment for same peg pathway is like hugely bumped up by filtering, as well as for coessentiality. I also want the same, like percentage of the same operon, which this filtering bumps up the percentage of interactions that are in the same operon to about half in the clustered case. This is not necessarily like a validation; it's more like a characterization. So there are a few potentially interesting protein complexes that sort of pointed out. This one involving TAT-A involves a lot of proteins that are so. TAT-A is a SEC independent protein, translocase protein. And then some of these other proteins are, so there's a putative ABC transporter also in this complex. So predicted to, and then there's an uncharacterized protein as well. So the nice thing about this complex is that TAT-A actually has a nice assay that that in TMAO glycerol, TAT-A doesn't grow on that media. So it could also knock out these other members and see if in that minimal media that they if the cells grow or not. And then there's another general secretion pathway. So potentially knock out these members of these secretion pathway, and there's one uncharacterized protein that's it's in between these two general secretion pathway proteins. So it might be important for secretion, which has a role in virulence. And
is the knockout collection available?
Is it irrelevant?
Is it available the collection?
Available now. There's a transposon insertion collection, so you can use that potentially.
But you could get the strains for individual knockouts.
So
somebody's probably done genetics on these. It's been.
But it says the uncharacterized.
Yeah.
the transposon for E. coli. Oh, yeah, this is maybe. This one does not have. Oh, sorry, I just unplugged my computer.
rather than
So I'm a little bit concerned about this. Like I said, there's about half of, and of course you can't see this at all, so it's kind of just going to be talk through it. But as I said before, that about half of the pairwise interactions are co-operonic. And if you walk through a lot of these operons, so for instance, these are so a lot of these complexes, the proteins are co-operonic, so they're shared. And if you look at the pathway there and the annotation that they have, you can they're in the same pathway. So you might look at these protein complexes as like, oh, okay, well, I'm getting reasonable complexes because they share the same sort of similar annotations. But if you look further, a lot of these protein complexes, they're in the same operon. So it could be that we're just like capturing with our data somehow we're overtraining two interactions that are in the same operon, and we're not necessarily capturing like true complexes. Yeah.
Have you looked at the illusion profile for some of these?
Yeah. So they're correlating at least strongly across at least 2 experiments for each interaction that's drawn. So it seems like they're sticking together, right? But I don't know. I guess I'm concerned about potentially it being like indirect interaction or like helping together. Or
the
like,
main concern is that you're using genetic distance feature
Yeah.
in there. And so there's this, you can't interpret co-operon stuff because that was a feature that we all have nice elements, but because that was over.
It's hard. So it's hard to like. I guess it's hard to assign confidence in the results.
It would make a lot more sense to leave it out as a feature and ask if it
Yeah,
but then you just
which I have done that, and it's just like, which I have that map. I've already generated that map, and it's much smaller, but maybe we're much more confident in that, and maybe we just go with that.
What's the distribution of co-operonic interactions in the reference set?
Yeah, so it's about how's that flat? Yeah. So the number of pairwise, it's a little bit over half. Yeah, sorry. It's I can move down 320 out of 560. All right, for the pairwise, 320. Yeah, so this is the on the y-axis the total number of proteins. Sorry, the total number of protein interactions. So there's pairwise interactions, and then this is for co-opronic. This is for the gold standard, so about 560. This is 320. This is the number that overlap. Yeah.
Not so simple.
No, yeah, no, but I think again, I'm just like kind of concerned because it's validation. Like it's hard to assign confidence, I guess, on the interactions. Yeah.
So these also, you're comparing E. coli workflows, right, as it goes.
Yeah, right. Yep.
But are they co-operonic in both the species?
So yeah, so I'm using the operons predicted from Pseudomonas to generate this plot. So that's an interesting question. I can see it, it's very different. My guess would be it wouldn't be very different. Because a lot of these gold standard proteins are considered across bacteria.
Using the broad observation.
How big these complexes this one again are? Like, could you be accidentally getting polysomes? And then that's why you see.
How big are the complexes? Yeah, so I have the,
I mean,
like as far as size.
Like, could you be pulling down huge polysomes and then you'd see everything in the upper end? See.
Probably. That's it.
Yeah.
But there, the separations are behaving rationally. And
Yeah.
you are seeing-
I have evidence that these interactions are real. I guess like maybe the way forward is just test some of them. I can test the interactions that come leaving out
You need to
the
put yourself-
operonic as information as a feature, and then
You need to put yourself in. I feel like the number of positive interactions from ecocycle is just so small that it's a really tough regime from a machine learning perspective, especially since it sounds like it's 200 roughly.
yeah.
And that the inclusion of the expression in quadratic features is complicating the interpretation of whether it's working actually or not. And again, because you come across it, so it's a test of it. So I feel that there's got to be a different framework for learning to bring a lot more features on, like using quadratic features as
So okay, that's a good transition.
okay.
So this is what I did this weekend, frantically, after having a conversation with Edward towards the end of last week, and so I used so maybe there's some other features, so some other target set that I can use to train on, and oh, this is not the right slide. I apologize. This is the right slide. So I actually use operons as a proxy because there's such an overlap between, since a lot of the gold standard proteins interactions are, in fact, co-operonic. Use operons as a proxy.
So now they're your training set.
Right. So now I have, instead of 500, I have 7,000 and positive interactions. And the question is, can we use this to recover gold complexes? And the answer is probably not really. And so this is a precision recall, and so the blue is the operonic holdout set. So for the training, I've subtracted all the interactions from the gold standard complex pairwise gold standard interactions. And then I tried to, and then the red is precision recall on the gold standard protein interactions, which
Okay, so now that's the episodic interactions. They're totally 100% independent from your training set. But these are real physical interactions. And your features are only cofractionation.
Only cofractionation
Only single numbers, so still with E. coli.
with E. coli.
So you're getting very high precision reconstruction. It's just going to be
So I'm really good at predicting co-operonic proteins.
And an operon holdout set here is the.
But the recall, like for reasonable precision, is like super low.
What's the blue person? This is like a test set on operons.
Yeah, it's a test set. So I did a 60-40 split on the protein interactions at the level of operons.
Okay, so that's interesting. So, so you're getting the blue curve traces the red curve for a while. Does the are the
It's
gold
like
standard interactions included in the operon holdout set, or are they removed from both?
no, they're removed from both tests and training.
Interesting. So it does feel like you're capturing something about co-operonic protein interactions at a very high precision regime.
Yeah.
And then maybe you're capturing expression relationships or something to pull in co-operonic relationships.
Yeah. Yeah, maybe. I don't really know what necessarily it's to make up a
how many interactions are in the kind of 0.8 and up regime in your full, whatever that score threshold is? To
Oh,
capture
so it's 10. So it's 60-40 split. So it's hundreds. So, yeah.
No, but not just running against your test set, but all predictions that you're making out of the classifier. All new predictions that you're making out of the classifier.
How many
above
new
that
predictions?
confidence threshold, yeah. Thousands of interactions.
Yeah, thousands. Yeah, like.
Oh, so that tiny little.
Oh no, for this. Oh, for this.
Yeah, I'm talking about
Oh,
0.8
no,
and
like
above
hundreds, like a couple hundred.
on your test set, but how many of the SPM making?
For this cutoff, for
that cutoff?
predicting all interactions, only a couple hundred.
Yeah.
For all
All predictions.
Use that cutoff, yeah.
Yeah, so hundreds.
Yeah.
So it is underpowered.
Yeah, kind of underpowered. So there's other things I could maybe try. I could maybe use like the chemical fractionation, like mass spec correlations to filter out interactions from the co-oponic ones, and like maybe co-expression or something to also like have a higher confidence in what we label as the gold standard for interactions using a co-oponic data or something like that. But it's not really
mass spec experiments going into it. From our experience in other systems, there should be more power in it.
I mean, it's just like that I'm an order of magnitude or less for the training.
Yeah, this is different.
So
The plus one interactions could be plus one features could be incorporated. They actually
And one thing that seems maybe a little different is that the long detergent treatments are kind of melting apart. Some of it, I had a similar experience that maybe you're getting more membrane stuff at the expense of breaking apart some that you can sort of say side-solid complexes. So you try subsetting out the.
well, I mean, I did feature selection, so I haven't specifically done that, but I've done it. Did feature selection to try to account for variables like that.
There was one feature for plus detergent and one feature for the minus detergent.
every fractionation is different.
Yeah.
Yeah, maybe combine them.
And then do the correlation.
Wait, so
Adding them and then correlate them.
yeah, so every single feature, yeah.
No.
That's
And that's easy to get.
yeah. I have a whole series of concatenations, and the larger concatenations are the easiest.
I guess I was nervous about adding tons of features because my training set is so low. I already have quite a large number of features. So I'm doing feature selection, so yeah, it could be okay.
You can plus the feature selection. Yes, you can.
Toss the feature selection.
Yeah, and I'm not sure that I would rule out the operonic, co-operonic access training regime. Because it's giving you this really high precision spike. And now you know that the interactions you're seeing are entirely driven from the program.
I think we had some way of like filtering out interactions somehow based on some evidence, like that are for the training set, both the positive and negative or something.
If we do the full set concatenated and the correlations. That's
Yeah,
what
adding more
I'm
features might help.
Yeah.
The matrix model, fractionation, so it's how often you see the first person across all fractions.
What is how often?
This is an observational picture.
They-
But there's no way to expect it.
Right, which you can just treat all fractionation experience as experience. And that shows pretty good signal.
Okay, so that's a hypergeometric probability.
That they're
That's a
co-observation.
Yeah, so it's a probabilistic
I see. Yeah.
I mean, there are some issues with it because there are not huge fractions in it, but it shows weakness in it for us.
Yeah, so that would be sort of a family of new features that give you more power. And there's always the question about borrowing the features by ecology because there's the big data sets and there is a lot of
Yeah, I mean, I can use those as features or something, or I can like, a lot of those interactions are captured in the string database, so maybe I can use like this string as a training.
Yeah, so I would sort of have a few standards on how to incorporate things. So
Yeah.
I think that restricting it to direct musical observations, like this case, is the sort of the principle.
As
Version of this.
features.
Yeah, as features, so that there is directly sort of the evidence that these two things do profile.
I was saying for like maybe like combine like use a string database somehow filtered to like
That probably is
as training cases.
possibly. That could be another way to run
I'm not gonna be able to really conserve now.
So you're saying that then all of that data is your training data, and then the operonic stuff is
Yeah, or like maybe like merge the Popron and the string database once, and like take the intersection on it, and then leave out the full standard. Something like that.
So I like leaving out the gold standard for it and then asking to construct defensive.
Closer to zero or something
I have a photo of that is probably not very readable because none of my pictures seem to be very readable, but E. coli is right here on the tree and Pseudomonas is right here.
of what the non-category.
Back up. That's bacterial.
That's panda.
It might be a little, I mean, I doubt this is what's hurting you, but I guess there are some problems maybe with the way that numbers to bacteria. Like there's so much going on transfer and all that. Types of groupings might be, I guess, sort of migrate down. And so you could just try to more strict orphalon detection.
I can see, yeah, sequence.
Yeah, I
Very
think
different.
confusion is interesting.
That's we'll check.
T-pallidum is the big set.
That's right.
What is T-pallidum? Is there a microbiologist?
I'm not really sure.
What is it?
Creepinema.
What is it?
Creepinema pellet. It's a spear sheet. It causes syphilis.
Is it
Yeah. It's a spirit sheet. Yeah.
Yeah.
Gram negative.
You say spirochete? Okay. But pretty different from E. coli.
Yes.
Yeah. I mean, I think it's like,
You list these other experiment types. There's no numbers, I guess you're not incorporating.
I don't, I mean, I just haven't gone through every paper. They have it varied as how many.
But there could be
experiments they've actually
some
done.
additional hundreds of experiments that can be incorporated.
Yeah, and I've tried to do some of that so far, and the precision recall looks like a mess. So I don't know what's going on there. I don't want to say too much about it. But, I just have had difficulty incorporating, and I suspect part of the difficulty is again just like being very underpowered.
Well, I think that
Also, like,
I mean, if
maybe
you're
I
creating
can-
hundreds of experiments with different species, T-pallidum was, I can't remember what they did.
They have thousands for
Yes.
chemical fraction, 2,000 or something.
Yeah, so that's a lot of data across a reasonably large phylogenetic distance. So with, as long as you're a pathologist,
Yeah.
that would be a much more. a lot of direct
Yeah.
evidence.
If you're gonna collapse all the way to the bacterial orthologous groups, then you may as well
So,
You're just gonna use
so what I did was I mapped onto Uniplot as the groups listed and for each protein, and I hold that.
So you take the Uniprot assignment to the numbers.
Yeah.
Yeah, that should work. You send it checks to make sure it's okay.
Yeah.
Yeah, it's just that if you're gonna just use E. coli and
You narrow it a lot, yeah. But that algorithm set was a really big aspect of experiments. And then E. coli, there's a ton of data that can be incorporated outside of ours. That's probably another 1,000.
So yeah. There's probably something weird about how I'm merging things, like merging the data, and that probably is a big part of my problem because I don't know. I might just like pick out the not like throw out all the yeasty hybrid ones and then.
So I would suggest incorporate all the mass spec data sets and do all the two hybrids as a task.
So does that become more of a bacterial complex map rather than Pseudomonas complex map?
Yeah. But I mean, whatever I can do to get good information out of the data, out of all the experiments that I've done.
Is that, are you going to be able to find Pseudomonas specific things that you could
I mean, if you did it that way, it
It would only be the conserved. Then we can test it in E. coli.
still be explaining some sort of biology, but probably not the specifics of the
yeah, kind of losing leverage for,
Yes and no, I mean, like the transporters and things like that. It's sort of classes. You could define, you just need to know something like
plus specific biology.
With the assumption that the proteins encoded within not single operands will form complexes. How safe is that?
I don't think it's safe at all. It's really binary basis. The observation is that the known protein complexes it has 50% of those. So it is a strong signal. You can often use noisy training data as long as it's got significant more positive examples. So co-operant data would probably use as a proxy for when you're training that against this infinite training which is
Yeah. You have to make some sort of compromise.
so I mean they're really bad example, 2 tiny example set or a large example set.
And it's possible that sort of strategy like won't work no matter what I do. It's possible.
Yeah, but remember, it's on entirely misspec replication. Yeah.
Yes.
Every expression is already like that.
Yeah.
So everything you're seeing is consistent with the pure factor. If there's enough sufficient data that these two things the fraction of these things I can think of more. I mean, the string intersection of all these things, they use the 2 hybrid as your string.
Yeah, it's not bad. It's something that it's like pretty good.
2 hybrid, right? So it's synergistic. It's half right on average, so it's actually pretty close to the co-operations.
Yeah, I mean, there might be ways like that's the string database. That's what I was saying. A lot of it takes a lot of interactions from these 2 hybrid these experiments actually. was a lot of fun.
Is there user confidence on the user out there to move from you just strictly really confidence?
Usually you can score them. Yeah, depends who did it. How they did it. Probably use them every feature because there will be frequent flyers. Frequent interactors.
Yeah, but you only it's the paintball is frequent flyers, but single bits. We got it's not like
Well, so if you take the case of a protein that has weak transcription activation activity, it's going to show up at normal interactions because it's a background association. So just in chance.
okay. So things are over.
Yes.
There's a way to get information how quickly machines been changing that way. Does that work for like with complexes?
Yeah, so like you're talking about using like if two genes like are always in bacteria, maybe they're more likely to be interacting than like two genes that are never, like rarely ever together.
So if you take non-complexes and interrogate them to see some evidence of fraction. So,
Sure, that makes a lot of, it's possible that unique bioinformatic features like that. Could like just looking at 5-year profiles.
sure, they're very powerful plenty of things that go function, but you don't necessarily make it. So that's
But is that used as a training? Can you use that as a training?
the simplest possible thing. If you can calculate
I have a comment that is not related to science at all.
Yeah.
But I think it's important.
Yes.
Yes, because you will presumably go to job interviews.
Yeah.
Right? Your slides need to be better. And in particular, can you go to one with the green stuff? Because there's a couple of important points that I want to make. Okay, so you're using a 16:9 aspect ratio, which usually already doesn't work out for some reason. But then you lose about 1/3 in vertical space for the title, right?
Sure.
So you have this tiny sliver, and that then forces you to use really small fonts and thin lines, and then it all breaks away, right?
Sure.
So make things bigger.
So, actually, I have a question, which is on the resolution of all of these, was it generated as a PDF on another tool and imported into the Mac, or was this directly generated in the Mac?
Sure. Yeah, I don't know.
So when I
It looked up. It's an import. It's probably like an import issue. I don't know, like because the images look fine.
was it open office, or what was it generated in?
What
software was used to generate
this
this?
is Google Slides. So Google Slides.
Google Slides.
But I think the projector doesn't have the resolution to resolve this small fonts.
Trivial. Yeah, absolutely. This is the, if you look at the large potential interesting complexes title, that's what it is. So I think that might have a resolution.
Yeah.
On the,
You go to the drive.
if you import it as a PDF or something like that, it's important to go.
Yeah, probably.
Yeah. It's like this should be like.
Yeah, you might see if there's some,
It's right angle.
but I agree that they should all be bigger.
Totally.
Yeah, and then
That's totally agree.
for some
agree
reason,
totally,
the
yeah.
16:9 format makes it harder to. You'd think, well, I have the same space in the middle and some on the side. It should be better. I have more space, but somehow it usually doesn't work.
Yeah.
I don't know. You've seen what 9 sides.
No, I mean, it doesn't fill the screen.
Okay. Is there? Yeah.
Those are
Yeah.